Hello. I will discuss the combined cycle power plant problem that we've been presented with in our class. In this project, we will build a model to predict the electrical energy output of a combined cycle power plant, which will use a combination of gas turbines, steam turbines, and heat recovery. Steam generators to generate power. We do have a set of 9,568 hourly average ambient environmental readings from sensors at the power plant, which we'll use in our model. The columns of our data that we're given for this assignment contains the following variables: temperature, ambient pressure, relative humidity, and the exhaust vacuum. We're going to try to figure out our dependent variable, which is the net hourly electrical energy output, which we're going to call our target throughout this assignment. Our background, a little bit of background. I tried to figure out, what kind of problem we're trying to solve, not just the data part, but trying to get a little better understanding of the problem. So the cycle power plant, the CCPP, is dependent on parameters which include atmospheric pressure, exhaust steam pressure, ambient temperature, and relative humidity. Multiple regression was used with machine learning to develop a model in order to predict the full load output power of a CCPP. I did find a nice picture of this, a combined cycle power plant, and I give credit to this link here, which is the Custom Control Sensor. They're a corporation. They did have a nice little description here. If anyone's interested, please go to this this link that I'm highlighting here. So in combined cycle power plants, the gas turbine shown in the upper left here, over here in the blue, generates electricity using natural gas fuel. Subsequently, the steam turbine shown in the middle generates electricity using waste heat from the gas turbine. This process is about 60% more efficient than other types of power plants, since the exhaust heat is reused to heat the steam turbine. Otherwise, it would be lost through a smokestack into the atmosphere. And again, here's the link for this if anyone's interested. I don't want to go too deep in this, but it has some good reading on this type of setup for a power plant. My project code, I'm going to make this a little bigger. It's a little hard to see. So my first thing I wanted to do is explore the data set. And also this is a Jupyter Python environment that I'm using for coding. Then I want to examine a correlation heat map and a bivariate distribution plot. Then I've decided, as I had mentioned, the dependent variable will be in my power output. I believe we call it PE, I did above. My independent variables are all those data that's collected by the sensors in the power plant. So I tried to come up with some different combinations to figure out a couple of models. So my first model is to select the ambient temperature as a possible predictor. My second model, I chose to have the ambient temperature and the exhaust vacuum as predictors. My third model, I decided to have ambient temperature, exhaust vacuum, and relative humidity as the predictors. And then my last model here, model 4, I said, let me select my ambient temperature, my exhaust vacuum, my relative humidity, and ambient pressure as the predictors, or my independent variables, right, into my multivariate regression. After I did that, I have to train my model with some data, right? So I have to take a subset of data. I obviously don't want to use 100%. So probably some folks are familiar with that. I believe it's called like a Pareto type of, choice that I'm making here. So I took actually 20% of the data for my test set, and I will use the remaining 80% of the data to train my model. My first regression that I thought of was a plain old linear regression. My second one is a decision tree regression. And my third one was a random forest regression. Then talking about my predictions, I looked at the root mean square error. The root mean square error, the RMSE, which will measure the average difference between a statistical model, predicted values, and the actual values. Mathematically, it is the standard deviation of the residuals. The residuals represent the distance between the regression line and the data points. My second one is a typical R squared, which is probably pretty familiar to everyone in basic statistics. The coefficient of determination, or the R squared, is a measure that provides information about the goodness of fit of a model. In the context of regression, it is a statistical measure of how well the regression line approximates the actual data. The R squared value will be in between 0 and 1. The closer we are to 1, the better the goodness of fit for the model. And my third one here is the mean absolute error, the MAE. The MAE is a measure of model accuracy given on the same scale as the prediction target. MAE is the average error that the model's predictions have in comparison with their corresponding actual targets. So here I ran some statistics here with my independent variables, my dependents. So I wound up having they're all floats, float 64 types. And the data did look pretty good when I saw it. I didn't see anything empty. And I had 9,568 rows. This is a heat map that I generated, which I'll talk about momentarily down below when I get to my text. This was for a correlation matrix. And again, I apologize as these screenshots are a little split up here. And then this was, I had started a bivariate distribution, which I will explain momentarily also. And I think I have a little better screen print at the bottom. I was getting cut off here. And this, oh, I'm sorry, I left my libraries in here. I was taking a look at what libraries I had loaded in Anaconda. So please ignore this here. So my objectives, I want to develop a predictive model to predict the full load power output of our CCPP. I'd also like to evaluate the performance of the models. My data source reference is Pinar Tufekci. This was given in our class, right? Prediction of full load electrical power output of a base load operated combined cycle power plant using machine learning methods. And it's found in this journal. And these are the references if you want to look this up and get this article. So as I mentioned before, we're using multiple regression, which is sort of an extension. Everyone's probably familiar with linear regression, looking for a dependent and independent variable correlation of a relationship. Multiple regression was used to build a model with our multiple independent variables: temperature, ambient pressure, relative humidity, exhaust vacuum, in order to predict our target variable, which is power output. And again, it's an extension of simple linear regression. It is a modeling method that uses multiple predictors or independent variables to predict a target or outcome, which we're calling throughout this document the output power, or PE. Our general form of multiple regression, probably everyone's familiar with y equals mx plus b from general algebra. Of course, this is a little more complicated. So I have my intercept here. Y is my target variable or power output. And my X's are my predictors or independent variables, which was my temperature, ambient pressure, relative humidity, and my exhaust vacuum in the plant. And again, B is my regression coefficients. The way I decided to tackle this, my steps or algorithm to predict what was going on with this power plant was to use multiple regression model. So first, I wanted to explore the data and analyze it. Secondly, I wanted to develop the model. 3, I wanted to evaluate how good the model was looking, or how efficient, I guess you would call it. And 4, I wanted to determine which model seems to be the best for my prediction. I think I had shown this a little bit before, but yeah, I explored my data. I had 9,568 rows, float 64 type. Nothing was null, so it was, fairly clean, or pretty clean, I would say. My distribution of my data set. I looked at, obviously, my count of my rows, my mean, my standard deviation, my minimum, my maximum, and my quintiles in between. The data consisted of four hourly average variables or features and a target variable, which is the output power, PE. Again, these are my ranges for ambient temperature, ambient pressure, relative humidity, exhaust vacuum, and my net hourly electrical energy output in the plant, which again we call PE. And hopefully everyone's familiar with these. These are centigrade, millibar for pressure, percentages for relative humidity, centimeters of mercury here, and megawatts. After exploration analysis, we needed to determine which independent variables will predict the output power. The regression will create a mathematical model from the features to predict the target variable PE. Selected features need to have a strong correlation, a high prediction capability within my target. A correlation matrix may be useful. And that was the heat map I had shown a moment ago, which I'll show again. The correlation matrix ranks the importance of predictors or input variables that have the most impact on my output or dependent variable. In order to achieve this, I'm going to plot the heat map of the correlation matrix using the Seaborn library in Python. So as we see, this is my heat map of the correlation matrix. A -1 shows that there's a full negative correlation, and a +1 denotes a full positive correlation. A 0 value denotes that there is no correlation. From the correlation matrix, we see that the ambient temperature and the exhaust vacuum have a strong negative correlation with my target variable, the power output, as their correlation coefficients are negative 0.95 and negative 0.087 respectively. The ambient pressure and relative humidity have a weak positive correlation with a PE with correlation coefficients of 0.52 and 0.39, so here. We can also visualize a bivariate distribution of the data set, which will show how each feature correlates to each other and our PE, our target variable. So we have a matrix, uniform matrix, ambient temperature, exhaust vacuum, ambient pressure, relative humidity, and our PE, which is our output of energy from the power plant. And again, on the x-axis here also, ambient temperature, exhaust vacuum, ambient pressure, relative humidity, and our PE, our target or dependent variable for the output of energy from the power plant. When we look at this, we can easily see that there is a pattern, a negative correlation seen on the AT, the ambient temperature, and the exhaust vacuum in relation to the PE, the output of the plant. Next, I wanted to develop my models. So My next step was to develop several regression models using different machine learning algorithms and different combinations of features. I decided to use linear regression, decision tree regression, and random forest regression algorithms on this data set. My feature selection. A critical part of the success of a machine learning project is coming up with a good set of features or predictors so that I can train my model on it. Feature selection involves selecting the most useful features to train on amongst the existing features. So first, I created 4 different combinations of features and trained our model with 3 different regression algorithms. Model 1, I selected the ambient temperature as the predictor, since it had the strongest correlation with the target variable, my dependent variable, the output or energy output of the plant. Model 2, I selected the ambient temperature and the exhaust vacuum as the predictors. Model 3, I selected the ambient temperature, the exhaust vacuum, and relative humidity as predictors. Model 4, I selected the ambient temperature, the exhaust vacuum, the ambient pressure, and relative humidity as predictors. And again, my target variable is the output of the plant in megawatts, and I just called it Y for my dependent variable. Before I actually trained our machine learning model, I had to split our data into a training and a test data set, which I was calling before, I think, the 20 and 80, right, in my code when I showed you a moment ago. The training set would be used to create the mathematical model of the relationship between the features and the target variable. The test set would be used to validate the model. To do this, we'll use the scikit-learn library and import the train test split module. So I did use 80% for the training set of my data, and 20% of the data went to the the testing. So I actually took this and I did it 4 times. Similar stuff. I made 4 models. If you look, we go back to the code. I'm sorry here for scrolling fast. I'm running out of time here, though. I think we have a time limit. Yes, so here I develop my models with my different right here in the screenshot here. Ambient temperature, exhaust vacuum, ambient temperature, exhaust vacuum, relative humidity, ambient temperature, exhaust vacuum, relative humidity, and ambient pressure. Oh, okay, I'm sorry, I had it here. Okay, we had it here. Okay, so we had linear regression. We trained on our model and our training set so we can make some predictions from that test set right here with our Y prediction. Then our second algorithm that we had used was the decision tree regression and random forest regression, noted below here. Decision tree regression, we trained it and then called up our test, right? And random forest regression, same thing, we trained again, and we called up our test. And a random forest, it's an algorithm that fits many decision trees and various subsamples of the data set. Predictions are made by averaging the predictions of each decision tree, and this improves the accuracy and control over a result. Our performance evaluation, whenever a machine learning model is developed, it's important that the performance is evaluated. So I tried to use 3 different items to evaluate that. As I mentioned, the root mean squared error measures the average error performed by the model in predicting the outcome. The R squared, that was between our 0 and 1. When you get to 1, it's a better fit or best fit correlation. How much variation in the target variable can be explained by the set of features in a training model. And our mean absolute error measures how far the predicted values are away from the actual values. So this was our results: the linear regression, decision tree regression, random forest regression. We see that the random forest regression algorithm model 4 gave us the best performance. The R squared was 0.9644, which translates to 96.44% of our variation in our target variable. The output of the energy in the power plant can be explained by the model. Also, it yields the lowest RMSE of 3.1891. So we conclude that our model 4 with the random forest regression should be selected. And this was just my code. And this was our data set from our instructor. And I guess this is just a bigger, a little easier to read than my screenshots. And thank you. I think that concludes my presentation. Oh, and also one note, I had used Anaconda with the Jupyter and Python for development. So the Anaconda gives a nice little dashboard here. I would highly recommend it. It has some different aspects here. Obviously for this, our little problem here that I just went through in presentation to solve our combined power plant problem, I used Jupyter. And as I said, I had used Python for my language. I know some folks might be want to use RStudio if you're using R programming, so that might be of interest to you. And there's some other things here also. And okay, thank you. And that's the end of my presentation.